Now we're in homework 10, problem 2. In this problem, we also need to explain some different kinds of stochastic processes. First is White-Sand stationary process. If a process has an expected value that is 0 and its autocorrelation depends on T1 minus T2 only, it's the difference between T1 and T2. It is a WSS process, White-Sand stationary process. And its expected value is a constant, and its autocorrelation is R tau. Tau equals T1 minus T2, the difference between T1 and T2. So this process has its expected value, which is 0, and which is 0, and its autocorrelation is only related to the difference between T1 and T2. So for this process, the constant should be 0. And if any process has this kind of expected value and autocorrelation, it's a White-Sand stationary process. So that's WSS process. The second one is independent increment process. We say that a process xt is with independent increments of the probability of these two guys and equals this. Both of them are independent to each other. So the probability is in this form for any non-overlapping intervals. So this process is independent increment process. Independent increments implies correlated increments. So such as there are many processes are independent increments, such as Poisson process, random walk, and the Wiener process. All of them are independent increment process because they are uncorrelated. Increments. So that's independent increment process. Next is Markov process. A process xt is a Markov process if the past has no influence on the statistics of the future under the condition that the present is known. For any n, and for example, for any n and T1 is more than T2 and it's more than Tn, n is a very large positive number. The probability of this process and in this form equals this. So this is the Markov process. From this, we can find that this is second order process. It can be this process can be statistically determined if one knows its second order distribution function f, large F, x1, x2, t1, t2. Because we have this, we know the probability of x1 and x2, so it can be determined in this form. Thus, a Markov process can be statistically determined by its second-order probability masses. The probability of the in this form for any I, j equals 1, 2, and a much larger positive number. So that's Markov process. Then is normal process. It's a kind of process that if random variables xt1, xt2, and xtn are jointly normal for any n and any t1, t2, and tn. So this is normal process. That is, the density function of x1, x2, xn, and t1, t2, and tn equals this guy. They are in this form, where x and x are in this form, and the expected value is a constant, and autocovariance is this. So that's normal process. The statistics of a normal process is completely determined in terms of its mean and its autocorrelation or autocovariance. So this process has different random variables, and all of them are jointly normal. So that's normal process. Next is strict sense stationary process. This process is different from wide sense stationary process. A real stochastic process xt is stationary in strict sense if its statistics is not affected by a shift on the time axis. What's that mean? This means that two processes xt and xt plus epsilon have the same statistics for any epsilon. So for example, if a process xt is SSS, which is strict sense stationary process, the density function of this x1, x2, xn, and t1, t2, tn equals to this. T is t changed to t1 plus epsilon and t2 plus epsilon and tn plus epsilon. And the density function of xt equals to this, and it's also equals the density function of x. The expected value is a constant if the constant exists. Also, the density function of this second order distribution should also it's also equal to this. T1 and T2 change to T1 minus T2, and the autocorrelation is this if the expected value exists. So from these examples, we can find that its statistics is not affected by the difference of time. So that's strict sense stationary process. So then is white noise. What is white noise? We define the process Vt, and Vt is a white noise if the autocorrelation is equal to this. And Qt, in this formula, Qt1 is the average intensity. So if any process has its autocorrelation which equals this which is in this form, so that's white noise. The white noise is a process such that its values at different times xti and xtj, I and j are positive numbers, and they are nearly independent. Actually, they are uncorrelated. So that's the experiment of white noise. So now finally, we are in mean ergodic process. We defined a process xt. Xt is a mean ergodic process if the limited with t to the positive infinity of this guy equals the expected value of this process. So that's the definition, and also the condition of this the process to be a mean ergodic process if the limiting value with t is t to positive infinity of this form of this guy equals 0. So that's the condition, and the expected value of this process must be a constant. For example, the expected value of is a constant, and also mean square sense means that the limiting number of this guy equals 0. So that's the definition and properties and understandings of mean ergodic process. That's the whole things of problem 2.